Today's lesson is going to focus on valence electrons. Valence electrons. So if you remember back, we were talking about the structure of the atom. We said that the protons and the neutrons were at the center of the atom in the nucleus, and then that the electrons were in this cloud surrounding the nucleus of the atom, and that they existed in these orbitals or these shells, or in these energy levels is how it's referred, sort of going out from the center. So the valence electrons are going to be those electrons that have the highest energy. So if you think about when we looked at the Bohr's model, where the nucleus at the center and then the electrons are sort of in those little orbitals or those orbits that are going out from the center, the valence electrons are going to be the ones that are in the outermost part of the cloud, the furthest away from the nucleus, if you will. Those are the ones that have the most energy. So the number of valence electrons in each atom helps to determine the chemical properties of that element. So however many electrons there are in that outermost region, or the number of valence electrons that there are going to determine the properties of the element, and it's also going to determine how that element will combine with and react with other elements. To show the number of electrons that there are in an element, we use what's called an electron dot diagram. An electron dot diagram. It basically just includes the symbol for the element, and then it's surrounded by dots, each dot standing for one valence electron. Before we start looking at how we're going to draw these, atoms will tend to be more stable if they have 8 valence electrons. We will see later that the number of valence electrons can be anywhere from 1 to 8. So, I guess that's up here. Different elements can have from 1 to 8 valence electrons. Because of the way that the electrons fill in these energy levels, you will only have 1 through 8 as the last, or the valence electrons. And when we get back in person, we're going to talk more about how these electrons configure. But for now, just know that the valence electrons, or the outermost electrons, you can have anywhere from 1 to 8. The more valence electrons they have, the more stable they tend to be. Atoms tend to form bonds so that they have 8 valence electrons and become more stable. So if they don't have 8, they will combine with other elements so that their combined outer electrons form 8 so that they become stable. So those outer electrons, so when they bond, those valence electrons can be transferred from one atom to another. They can be gained or they can be lost, or they might be shared between the atoms. And this causes a chemical bond to form, which is the force of attraction that holds atoms together as a result of the rearrangement of electrons between them. So they might give away an electron, they might gain an electron, or they might share electrons with other elements. So the way that these electron dot diagrams are drawn is you just know the number of valence electrons that there are, and then you just kind of begin putting dots around the symbol for the element. It looks here like their pattern, and I'm not going to be too picky about the pattern, the way that you do these, but it looks like the pattern that they do here is to place the first electron to the right, and then just they filled them in going counterclockwise from the right to the top, to the left, to the bottom, and then circle around again, right, top, left, bottom. Hydrogen only has 1 valence electron, so we put the dot to the right. Carbon has 4 valence electrons, so we go 1, 2, 3, 4. Oxygen has 6, so we go 1, 2, 3, 4, 5, 6. And since the most that you can have is 8, you would then go here next and then here next to fill in for 8. So you have neon given as an example here. So look at your periodic table. Find neon, which is number 10 on your periodic table. There's a periodic table on the next page on 126. So if you look on page 126, find neon, which is number 10 on the periodic table. Neon has 8 valence electrons. So when we want to put in the valence electrons, we would go 1, 2, 3, 4, 5, 6, 7, 8. And that would be the electron dot diagram for neon. So we can apply this information then to the periodic table. We know from what we've talked about already that the atomic number increases as you go from left to right. That means the number of protons increases, which also means the number of electrons increase as you go from left to right. So therefore, following that, the number of valence electrons will also increase from left to right across each of the periods as you go across the periodic table. Each period, remember that's a row, that begins with an element that has 1 valence electron. So that means that everything, each period, begins with an element that has 1 valence electron. So all of these would have 1 valence electron. And then except for period 1, a given period ends with an element that has 8 valence electrons. So that means that all of these, because it says except for period 1, all of these would have 8 valence electrons. And that's because if you look at helium, it only has 2 electrons, so it couldn't have 8. But it is a full energy level, and that's what's important. So everything in group 1, with the exception of hydrogen, we'll talk about in a moment. So everything in group 1 has 1 valence electron. From 2 through 7, they need a lot more in order for their energy levels to be full. If you look at group 18, they are all full. And we will see why that is important a little bit later. This repeating pattern then means that elements within a group always have the same number of valence electrons, so therefore they have similar properties. So we talked about earlier that groups of elements all have similar properties, and that's because they have the same number of valence electrons. Hydrogen and helium have these slightly different characteristics about them. On page 127, I want to stay on this page for just a second so I can draw on this, but on page 127 it tells you up the top that group 1 elements have 1 valence electron, group 2 elements have 2, and then it jumps over to group 13 saying that they have 3, 14 has 4, and so on. And that is because these transition elements here in the center of our chart, these behave slightly differently. They have a slightly different pattern to the way that their electrons fill in. So we'll come back and talk about those another time. But for now, let's know that group number 1, everything in group number 1 will have 1 valence electron. Everything in group number 2 will have 2 valence electrons. Now they've skipped 13 and 15, they're just talking about these in general. So 14 would have 4, 18 would have 8. So likewise, 13 has 3, 15 has 5, and so on. So here are a list of some of the elements. These are the elements, basically 1 through 18, and you can look at how their electrons fill in, their valence electrons fill in, basically do those models that we talked about a few moments ago. So I'm going to have you do these kind of tonight as homework. So I'm not going to jump into these right now. I'll give you an explanation tomorrow. But basically, look back at your periodic table, what we just filled in. You know how many valence electrons each one of these would have based on where they're on the periodic table. And then just fill the dots in going around like we did earlier. So there are a few groups that I want to talk about on the periodic table specifically. So the noble gases, if you remember, are all of those elements in group number 18. The noble gases, which are group 18 elements, those are atoms with 8 valence electrons, with the exception of helium, which has 2, but it is a full. The last energy level is full. Because they are full, they are very unlikely to gain or lose electrons or share their electrons with other atoms. So therefore, they do not react easily with other elements. We typically find the noble gases as standalone elements, and they don't typically mix or chemically combined with other elements. Metal atoms tend to react by losing their valence electrons. So in general, the reactivity of a metal depends on how easily its atoms lose its valence electrons. And just like with everything else in the periodic table, there is a pattern, and the reactivity of metals decreases from left to right across the periodic table. So those metals that are on the left-hand side of the periodic table are going to be more reactive than those that are on the right-hand side of the groups of metals on the periodic table. And that's because those on the left only have 1 or 2 electrons. They need a lot in order to be full, or in order to be happy or complete. Those that are on the right-hand side are nearing being full, so they don't react as much because their shells are more full. The alkali metals then, group number 1, is going to be the most reactive element in its period. So at the periods of the rows, so in each row, the group 1 elements are the ones that are going to be the most reactive. Nonmetals become stable when they gain or share enough electrons to have 8 valence electrons. So they usually, the nonmetals, usually combine with metals by gaining electrons. So we just said that the metals tend to lose their electrons. The nonmetals tend to gain those electrons so that they can combine with the metals in order to combine and form compounds. Nonmetals can also combine with other nonmetals and metalloids by sharing electrons. So the nonmetals will gain electrons from metals in order to combine with them. They will share their electrons with other nonmetals or metalloids in order to make compounds with them. The halogens, remember, is group 17, react easily with other elements. And that's because they're almost full. They need 1 electron to make them full. So typically what we will find are the halogens in group number 17 will react very easily with group number 1 elements, because group number 1 elements have 1 electron to give. The halogens need 1 electron. So they tend to combine naturally quite often in nature, just based on the numbers of electrons that they need and that they have. The metalloids then can either lose or share their electrons when they combine with other elements. And that's because metalloids tend to have some properties of metals and some properties of nonmetals. So they're going to behave sometimes like metals, sometimes like nonmetals. But they can either lose or they can share their electrons when they combine with other elements. Hydrogen, again, is sort of its own little group. It's placed in group 1 because it has one valence electron. But again, hydrogen only has one electron. So even though it only has one in its last shell, it's still full because that's all that it can have. Hydrogen is considered to be a nonmetal. The properties of hydrogen are very different from the properties of all the other alkali metals underneath of it in group number 1. But it does share its electron when forming compounds with other nonmetals so that it can get that stable arrangement of 2. And we'll talk about why 2 again later. All right, so again, if you would go back to page 127 and fill in those valence electrons for the elements, nitrogen, oxygen, fluorine, sodium, magnesium, aluminum, silicon, and argon, and do all of the other in-text questions for pages 124 through 129. Thanks for listening, guys. Have a great day.